All right. So it is now 2 o'clock, so I think we will get started with this webinar. So yes, welcome everybody to this webinar and thank you for joining. So today I will be speaking to you about or giving you an introduction to CFD with ANSYS. And my name is Tim Tostrup Hübschmann and I work at EDRMedeso as a CFD engineer. So there we go. So the primary topics I will be speaking about is I'll be showing you the new user interface that Fluent has been given. I'll be showing you Fluent meshing and some expression that has finally been implemented into Fluent. And then we'll touch upon some new models, some turbulence modeling, and the new cool VOF-to-DPM approach that has been implemented a couple of releases ago. Then I will demo the new Fluent workflow for you, and we will end the webinar series with a Q&A. So let's move on. So Fluent has been given a lot of attention lately on this experience that you get when you use Fluent and on the GUI. So there's been done a lot of work and a lot of the GUI has been sort of reinvented within Fluent, and a task-based workflow for the Fluent meshing has been implemented, and just a lot of tasks to improve speed and simplicity within the Fluent environment so that you get to do a lot more CFD in less time, of course. So one of the first things is the new look. So you can now choose from a couple of templates. You will have the new Fluent look, and you will have the possibility of going back to the classic Fluent look or a space claim-like look. Yeah, basically themes for your Fluent GUI. Also color schemes, which you can pick and choose from, especially for post-processing. Some of you are used to some other schemes, so you can choose those from the Preference tab. Regarding the new task-based workflow that has been implemented, it's basically implemented to sort of streamline all the tasks that you have to do when you're meshing. So, and also while you're doing these different tasks, you get a lot of good best practices. So when you do the meshing, you will get a lot of help with the meshing on if you have to do inflation layers and default sizing values and stuff like this to help you on the way. And it's also really good to do repetitive tasks, so you can sort of record what you've done with the mesh, and then you can repeat that again automatically with your next task or with your next CAD, as long as it's similar, right? As long as you need to do the same tasks. Yeah. And also the full access to Fluent Power. So here, the meshing part has also been parallelized now. So even though Fluent is known to be really strong on the parallelization, Fluent meshing is also really strong on the parallelization now. And one of the main things that's sort of behind this is the Mosaic technology, which enables you to do different surface mesh, different bulk mesh, and sort of combine them conformally from the boundary layer until the bulk mesh. So what we're seeing here is a poly surface mesh with some prisms and poly cells connecting to a hex cell and some hanging nodes as well. And the reason for this is the flexibility of doing such a mesh that you can first do a surface mesh and with curvature setting or body of influence of what you want to do, and then combine that with a hex mesh in the bulk, which is of course very fast to solve on. Yes, so this is just to highlight the different aspects of it. So of course you ensure that you have a high quality in all of these areas within the poly cells, which has become sort of the standard mesh that you do nowadays due to fewer cells than when you do triangular meshes. And then you have the hex core, of course with high quality, because this is only hex elements and fast solve times on those, and then conformally connected with this Mosaic technology. So the parallelization that I spoke about, it's the meshing port is parallelized up to 64 cores, which can provide you up to 10 times faster meshing times. For this combustor here we're looking at here, then it's up to 10 times. And this really can enable people who are spending a lot of time meshing. Because people are using a lot of people have a lot of clusters now, so they can solve the solve time is not really the limiting factor. Sometimes it becomes the meshing or the post-processing, and now the meshing is not the limiting factor anymore, at least not when you use Fluent meshing. One of the other cool features that was enabled in this release is conformally connecting the 1 to 8 hex core cell size jumps here with Poly-Hexcore, and this ensures that you get accurate results. So some people have had issues with the cell size jumps, so you have a 1 to 8 volume ratio between these hex elements, but now you have the possibility of connecting those conformally with these poly cells within the Mosaic environment. So this is really cool. So just to give you sort of a walkthrough of this single window workflow in Fluent. So of course you need a geometry, and this is not yet in Fluent and will not ever be in Fluent, I think. So for that you need your own CAD model, or you could have a space claim, for example, which is what I'm using and ANSYS is using. The next step is to import that into the Fluent meshing. And then the first task that you're prompted to do is to create a surface mesh. So then you'll create a surface mesh with a high quality surface mesh. And from the surface mesh, you will do a region extract. And within this Fluent meshing, within this task, you're actually prompted to do sort of capping. So if you did not enclose your fluid volume inside space claim, if you did not do a volume extract there, then it's possible to cap those within this workflow in Fluent meshing, and you can continue from that on. So that way you're able to do the volume extract, and after the volume extract you will have to do the volume mesh. And those are basically the tasks that you're prompted to do when you're doing this, when you're using this Fluent meshing workflow, task-based workflow. And then you continue to set up solve within the same GUI and post-processing as well. So this should sort of ease a lot of, ease the use of Fluent a lot. At least it has from my point of view. This is for now only supported as standalone. It is beta in Workbench, so this task-based workflow, you can activate it in Workbench through the Properties tab if you want to use it and do parameter studies and stuff like this within the Workbench environment. It should be supported for the next release, which is in a couple of weeks. So you can look forward to that as well. So yeah, the high quality meshes here. So basically you're saving, it's 70% faster. And I have to admit that I did not test this myself if it was exactly 70%, but what we see is that you do a lot less clicking. So in the old workflow, you would have something like 400 clicks, and with the new workflow, you only need to use 40 or 50 clicks in order to do the same mesh. So that way you're using a lot less time. Combine that with the parallelization of this Mosaic technology, you're saving a lot of time. Yeah, and of course this is also very helpful to new users. You need a lot less training in order to be able to do these nice and cool meshes, of course, with these workflows. One of the things that sort of when this workflow was implemented is how should it be implemented? Like what sort of tasks do we need to do? Which tasks are most common? And we sort of implemented those. But this workflow is actually, you can change this. This is a simple template actually that you have here, so you can add extra tasks, so you can add refinement tasks or journal scripts actually within different tasks here, and save that new workflow and give that to colleagues if that's what you wanted. Yeah, so you're also able to record and replay your workflow. So here we're looking at the describe geometry tab, and there you prompt some questions, and these questions will change depending on the situation, depending on the geometry that you've imported. Yeah. The updates for the last release for this workflow was to add some local sizings. So just after you've imported geometry, you're going to add some local sizings. So now you're able to do face sizing, body of influences as well, and curvature and proximity settings on local faces or edges for that matter, just like people are used to do in ANSYS meshing. So this is very similar. Then there's periodic boundary support now. And if you're working with assemblies, then you are now able to import these and perform the share topology task so that you get elements to share nodes within the workflow. And then of course the parallel option. So this is still quite new, but it's really robust. So just go ahead and use that for the Poly-Hexcore. And then field level help. So for each task, there will be a help icon to sort of guide you whenever you need that. And then within SpaceClaim, so this is not within Fluent, but within SpaceClaim, you will have a Fluent button so that you will go straight into Fluent from SpaceClaim. Then, of course, as I said earlier, Workbench is only in beta supporting Workbench. So an example of using this, some examples of using this parallel meshing technique here. For a mesh in the region of 10 to 20 million cells, you can get up to 2.5 million cells per minute with 16 cores. And it requires 3 GB of memory of about 3 GB of memory per million cells that you're generating. So you need some memory as well. This button here is only showed within this watertight geometry workflow, and this is to ensure the robustness of this. So it's not really, you're not really to use it anywhere else than within this workflow. One of the really nice things about this is that it does not use any ANSYS HPC licenses, so you do not need more HPC licenses to do this parallel meshing. Yeah. I need to click on the right window. There we go. So another test case here for parallel Poly-Hexcore test case is this combustor, where we see that from, if we go at around 8 cores, it's about 1 million cells per minute. And then if we go to about 55 cores here, it's about 7 million cells per minute. So you really get a good speed up here. And you don't even lose quality. You're actually improving the quality by going up to several cores by using the standard workflow. And this was 38 million cells. So you need some million cells in order to really utilize this parallelization. But I think this is really impressive. So here we have a Formula 1 car where we have tested it. So that's 220 million cells. So in serial mode, you would have used 8 hours for the meshing. With 64 cores, you're down to about an hour of meshing time. So you're really saving some time here. 7 hours on the meshing tasks. Another workflow that's in beta right now is the fault-tolerant workflow. So if you have what we call dirty cat, then you're able to do this with a workflow as well. So this was really cumbersome when you wanted to use Fluent meshing before. Of course, Fluent meshing has really been strong on this point as well to do these dirty cats, but it's been for expert users to do this kind of tasks. And now you're actually able to do this within this task-based workflow, so the fault-tolerant workflow, it's called. And one of the really nice things about it is that you can go back. So once you've made a, let's say you fixed some proximity, or you added some local sizing here to the edges, and then you did the surface mesh or prisms. But now you need to change this. In the old way, you had to, if you didn't save that, you would have to go all the way back. But now you can simply jump back to that task and change that and click update on the prism, and it would go back and update from the beginning and forward. Yeah, so it's also been sort of a little neat feature is that you can now do selective mesh check for the different, whatever you wanted to check. Phase handedness, for example, you could simply click that and have a look at that, or select all. That's really up to you. A time saver now is expressions. So now people won't have to use UDFs. Of course, UDFs are still very useful, but now expressions are in Fluent and fully supported. So you can both do functions of locations, for example, of an inlet, if you wanted to do some form of parabolic inlet here, a velocity profile, function of time, solution variables. You can do you have physical constants available and different mathematical functions, so sines and cosine, and you can even do if-else statements inside this expression environment. And I'll also show you an example of that later. Yeah, and this is very similar to what's already implemented in CFX and AIM, if people are used to those. So an example of how much time and you're saving is the new expression allows you, for example, if you want to do a sinusoidal outlet pressure here, that you want your P out to be a P naught and plus a fluctuating part here, P of T, then you would have the P naught, and then you would have the P of T, and simply just write that frequency straight into the expression. If you wanted to do this implementation in UDF, you would have to write all this C code here, both incorporating C and also some Fluent specific programming. For example, these thread and position and stuff like this, you would need to know this as well. So you're really saving a lot of time there as well. So here's how it's implemented. So for you can create the named expressions. So here we are looking at the expression P varying, where we see the sign to the frequency that you want to have, and then just put that in. So you're even writing an expression within the field. So you're using an expression. You're making an expression with an expression. So it's it's really helpful. So if we have a look at this video here, Okay. Okay, so I'm just gonna do it like this so that you can see the video because it's quite cool. Here we go. No? Okay, moving on. So another step here is, or another thing that's really been improved is the way that you do mesh adaption. So you now have separate criteria for refinement and coarsening of this adaption. And what's new is that you now have buffer layers as well. So if we look at these bottom pictures here, we can see that we have, for the first one, we have one buffer layer, and then we can see that it's increasing with the number of buffer layers. So the cell zone register, so where we're doing the adaption, is sort of increasing with these buffer layers. So this is again to sort of save a lot of clicks and to ease it for the users. So we're all these windows that it was before is simplified down to 2 windows. And yeah, you have your register of your definition. Here you have the name. So in the case below, it would be top fill gradient 0, and you would have selected a type here and the derivative. So here you would specify if it's a gradient adaption or a min-max value adaption, and whatever value you wanted to adapt. So velocity, temperature, whatever you wanted. And then in the adaption criteria, you will be able to select those that you've created here with the field variables, one for refinement and one for coarsening. Yeah, so what I spoke about before is that the gradient adaption and ISO value adaption is now consolidated into one window. So for the top part here, you see that you have cells in range, less than, more than, outside range for the type, and then the derivative option, you have gradient and curvature, and you have some scaling options as well to pick from. Yeah. Another time saver, or I'm not sure how much people use it, I've used it a couple of times, is it's kind of annoying that I can't play these videos, is that you can now do a drag and drop. So give me 1 second and I'll try to reopen this presentation. All right, now it seems to work. So that's good. So now we can have a look at this sinusoidal pressure as the first movie that didn't work before. Yeah, and this is implemented with the expressions. So that's really cool. So let's move on to the next one. Yep, here we go. So we now have the possibility of doing drag and drop between different Fluent sessions. So here you see copying of the boundary conditions and just dragging them on top of a boundary condition, of the boundary condition tab. And then it will identify by names and that way implement those boundaries. What you're also able to do is to drag an inlet on top of an outlet, and that way it will change that specific boundary. So now it changed an outlet into an inlet based on how you drag and drop. And you also have the possibility now to copy to clipboard, and that way copy your boundary settings into an Excel sheet, for example. And that way later you can import this into your next session. Yeah, to faster get your boundary conditions, so you don't have to click all the boundaries. Yeah, so here you see how to sort of export or import from a file. So you would select the boundaries and then import from whatever file you had. So this should also save up some time if you get used to working with it. Some people still use the TUI command language. It's still really good if you want to automate tasks again. And now you have the possibility of using autocomplete. You need to enable it in your preferences in order to have this autocomplete of the TUI commands, but this is really helpful as well. The surfaces are now exposed, so if you did a ISO surface that you wanted to plot on or something else, then you can now go and edit this. This was not possible before version 19.2, but now you have the possibility of editing that and change the ISO value or however you created your surface. So this is really good and also necessary for post-processing. Another user enhancement is this progress indicator. So now you don't get this little box saying stop solution. Now you have it as a progress bar at the very bottom of the Fluent GUI. What you're also seeing is that you now have the possibility of starting a server, and this is very similar to what CFX people have been used to, that they now have, that Fluent now has this remote visualization client available, so this thin client. And this looks like a bit like this. So now you can interactively monitor and manipulate a Fluent job on a remote cluster. So and you basically connect to it through a small text file. And you can do new plots and have a look at contours, vectors, path lines, whatever you wanted to do. You can even change a few settings, stop the simulation, change time step, and start it again remotely. Yeah. Yeah. Just so people know, there's been a change to on the solver side of Fluent. So now the couple pseudo transient solver is default for most cases. This has sort of been stolen from CFX, but this is standard now and default. And some other settings regarding coarsening has been changed as well to get better convergence. Yeah, and a couple of other changes as well. This reach-out flux formulation had to be changed due to this new mosaic meshing, but that's fixed and works really good. You have the possibility of doing of activating prevent reverse flow on inlets. For some cases, this is, or for some versions, of older versions, this is a beta feature, and you will have to activate beta features to have this available. You now have some text commands as well to help you with periodic interfaces. Yeah, new turbulence models. Florian Manter, the turbulence guru at ANSYS, has developed a new model, a generalized K omega called GEKO. And the really cool thing about this is that you have tunable parameters. So before, if you knew that your sort of mistake lied within the turbulence model, then you really had no chance to sort of change this, because if you change those parameters for the K omega SST, for example, then your simulation would crash. But now we have these 4 coefficients, free coefficients they're called, that you can change to sort of change the behavior of the turbulence models. So you can change separation or spreading or near wall behavior and some optimized free jet flows. And of course, there's further explanations in the help about these coefficients. But just to give an example, here we're looking at an aerofoil, and the experiments are the dots, and the standard SST model is the blue line. And we see that by using the GEKO and a coefficient of 2.5, then we match results much more closely than just by using the standard SST. So there's now a way to tune your turbulence models to accommodate results. The last thing I want to show you is this, it's not new anymore, but a really cool VOF-to-DPM approach. So if we have this interface here that we're tracking, and we're capturing sort of large structures with a WOF model, then we also need a really fine mesh and small time steps. And then we have a region here where we can actually use the DPM approach and use a much coarser mesh and larger time steps to use less computational power. And then we have a region here where we have a transition from VOF to DPM, and this is now implemented into Fluent, dependent on some diameter criteria that you're specifying and sphericity. And I think this is a big time saver for people. I even think that people with problems like this would not even try to solve these type of problems because they would be too computationally expensive. But now there is a sort of a halfway to do this kind of simulation. And just to show a nice video here where you see, of course, the particles are exaggerated, but where you see the VOF model here and the transition into DPM, so parcels, and they're a bit exaggerated, but you can see how it works. Yeah. All right. So that actually concludes the slides that I had. See, that's right. So let's go to the demonstration case. So what I've brought today is a mixing elbow where we have two inlets and an outlet. So what I'm going to do is I'm going to do a cold inlet and a hot inlet so that we can see the temperature distribution inside this mixing elbow. The way that I like to work is that I like to do as much of the pre-processing as possible in SpaceClaim. And for a CFD analysis, I need the fluid domain for this part here. So what I'm going to do is that I'm going to go to the Prepare tab and use the volume extract. And then I'm going to select these capping surfaces here. There we go. And I'm going to select a seed face as well. So now by clicking this V, SpaceClaim simply gives me the fluid region within this geometry here. There we go. And what I can now do is I can also do name selections. So I want this, I go to groups, go to create name selections, and I call this inlet big. And I go to the small one here. Oh, there we go, create name selection, inlet small. Go to the end here and say outlet. Now I'm only missing all the walls. So what I can do is that I can select all my name selections here. I can right click, go to face, and I can hide my faces. So now I can simply drag over all the geometry that is there and create a name selection and call it walls. So now I've named all my geometries, and I can show everything just to be on the safe side. And what I actually wanted to do also was that I wanted to have a refinement region near my mixing here. So what I'm going to do is I'm going to draw a box here. There we go. And then I'm going to pull this. And when I do this pull, I need to remember to activate no merge, or else I will simply just merge the geometries right away. So I think I'm going to do a box like this, and I'm quite satisfied with that. I could go and do a view as I did before. So this cut view here, and I can actually work within this cut view as well. So I could do a pull on this surface again to sort of see where I'm at. All right, so I'm gonna go back. And then I'm gonna name this. Oh, I need to go to, then I'm gonna name this BOI. So what would happen if I imported this into Fluent meshing? Right now, I would import all the 3 bodies that I've generated. But for this simulation, I don't want to do conjugative heat transfer right now. So what I'm going to do is I'm going to right-click this geom solid here and say suppress for physics. So now this solid won't be imported into Fluent when we do that. So I'm just going to do a quick save. I'm going to close my, and then I have the possibility inside this workbench tab to go directly into Fluent here. So I can go to Fluent. I can say this watertight geometry workflow. I'm going to click on that. And this, we can see here, this launches Fluent in serial mode actually. So if I wanted to use several cores, I would have to open up Fluent in standalone. The way I would do that is that I would find Fluent here, and I would be prompted with this window here. And here I have the possibility of activating meshing mode, and then the number of cores that I wanted to use for that, that meshing part. Yeah. So let's just stay with this here. So first off, the geometry was automatically imported because we did it directly from SpaceClaim. And now I have the possibility, it asks me if I want to do local sizing. I have the fill help here to help me choose whether or not you want to add local size controls in order to create surface mesh. So here I can say yes, because I have my BOI. I'm going to call it BOI. Growth rate, fine. Face sizing, no, it's a body of influence. And then the target mesh size of this body of influence. I'm going to give that a target size of 6. And then I'm going to go to the BOI part here and add that to local sizing. So now I can go to the surface mesh and I can already have a look at these sizings. So the size field. I can see that the smallest mesh size is maybe a bit too small. So I'm going to increase that to maybe, yeah, 1 is maybe okay as the smallest size here, as I want to capture some of the curvature. And then the biggest size as well, 10, that's maybe a bit too big, maybe just 8. I can sort of work my way through all these parameters. And then we have the size functions. So here I can specify curvature or proximity, or I can specify both. So I'm going to specify curvature of 15 degrees normal angle. And then I want a minimum of 3 cells across gaps. But right now the scope is only 2 edges. So if I want to ensure that I have 3 cells here in this inlet pipe here across the gap, then I would need to scope it to faces and edges. And then I create my surface mesh. Hopefully my settings are right. Yeah, that looks okay. So we don't really see the refinement region very well. So what I could do is that I could go back to my body of influence, revert and edit, and give this a 4 instead, and update that, and create surface mesh again. Now we see how the BOI has had an influence on the sizings in the so in the location where it was lying. So now I'm quite happy and I'm ready to move on with my mesh. So the next task I have to do is I have to describe my geometry. So here I need to set the right settings here. So the geometry consists of only solid regions. That's not true. The geometry consists of only fluid regions with no voids. That's true, so I'm going to select that. I don't have any internal walls and I don't have any shared topology. So that's the way I'm going to describe my geometry. Fluent automatically, just by looking at the names, prescribes boundary types. So I can change these if this wasn't correct. But this is right. I want 2 velocity inlets and I want a pressure outlet and the rest is walls. So I'm going to update those boundaries. Then the regions. So if I had multiple regions, then I would have those lying below here. So I'm going to update this region. And now I have the task to create my volume mesh. So standard settings here is that on all walls you will have inflation layers, and the standard setting is what's called smooth transition. You also have uniform, last ratio, and aspect ratio offset method types that you can choose from, and the number of layers. So I'm just going to keep that to 3. The transition ratio is a default Fluent value. If you want to do the mesh, Fluent meshing, and import that into CFX, then you would need to change this value accordingly. Then we have the fill width volume setting. So the default one is polyhedral, and we can try to do a polyhedral mesh real quick to see how that looks. It's really loud. There we go. So now we have our polyhedral mesh here. Oh. And we see that the BOI has really influenced the mixing region here as I wanted to. So this looks good. I could continue with this, but just to show you, then I want to use the Poly-Hexcore setting here, so the Mosaic technology. And right now I don't have the enable parallel because I opened up Fluent meshing in serial. But if I had opened up in parallel, then I would have the checkbox of parallel, and that's also on default. So let's update this. So we see the boundary layer being created first, and then it moves on. So here we have our Poly-Hexcore mesh with a really good quality. So 0.02 maximum skewness, orthogonal quality of 0.28. So this is very satisfying and a very good mesh to continue our calculation on. So I'm going to continue with the solution. I'm going to switch to solution. I'm going to say yes. And right away, I'm opening up the Fluent panel, as people might be used to see it, the Fluent solver panel. And what I'm going to do is I'm going to specify energy, and I'm going to activate the K omega SST for turbulence. So there we go. So now I need to specify my inlet conditions. And what I can do now, what's available, is to simply click here on the inlet boundary, right click and say edit inlet big. So it's also automatically opening it up over here so that I can see what I'm clicking on. So I'm going to specify a velocity magnitude of 1 meters per second. I'm going to click my small inlet here, edit inlet small, velocity magnitude 1 meters per second, and then I'm going to change the temperature to 360 Kelvin instead. I'm going to click the outlet, and I can see that's already a pressure outlet, so that's fine. And already now I'm ready to solve my case. So I'll go to solution, I'll type in a couple of iterations here. Let's just take 25 and calculate. And automatically the initialization will be done with the hybrid initialization with 10 iterations, and move onwards to calculating my CFD solution. And in the bottom here we see the new bar, new progress bar. So we're at 32% now, continuing. And we also see that we had the possibility of starting a server here if we wanted to. Some of the other cool things that has been implemented now, I'll show you when it's finished here in 2 iterations. There we go, thank you. Is that you can filter your search tree over here. So if, for example, I wrote inlet here, then I would only be looking at inlets. So if you have been smart in your naming, then you would be able to sort of identify phases with a certain condition, and that way save a lot of clicks over time. You also have this quick search bar up here in the top. So if, for example, I didn't remember where the mesh adaption tab was, I could search for adapt here, and I can see here where these different, so it sort of highlights where that section is for the adapt. And it also gives me some idea about the TUI commands that I could use. A thing to note is that if you want to do mesh adaption on the Poly-Hexcore, then you have to use the Puma algorithm, which is not default in the Fluent session here. So you would have to do that, but you will also be prompted for that if you do adaption, so that's fine. Let's have a look at some results. So first off, I'll create a surface. I'll create a ISO surface. And in order to do this, I'll just quickly display my geometry. So I want to have a cut plane through here. So I'll do mesh, set coordinate, and I'll compute to see the minimum, maximum. I can see 0 is right in the middle. So I'll click create here. And now I'm ready to do contours on that plane. So let's do temperature on that plane. There we go. And this looks really good. There's of course ways to sort of improve the look of this. We could go to the mesh here, say new, and create, let's just pick the walls here. Let's not pick the edges, and let's say save and displace on this one. So now I have 2 sort of views. I want to view at my mesh. I also want to view this contour plot at the same time. So what I can do now is I can create a scene here, and I can activate both and put some transparency on my wall. This way get a cool look of how the walls also look with my contour plot activated. And a lot of work has been done on doing this drag and drop feature. So if I wanted to show just show the contour, for example, then I could drag and drop this. So now I'm showing 2. So let's just display this. If I wanted to show the contour within this or with this mesh, then I could just drag and drop, and it would add that to the graphics. Yep. So the last thing I wanted to show was the expressions. So right now, what I implemented for the inlet was a simple uniform profile of 1 meters per second. But what I could do is that I could create a named expression here. Let's call it V turbulence. And then for the definition, then I've cheated a bit. So I will copy and paste here. And what you see here is that I have different units. So here I have 1 meters per second time this function here, where I'm using millimeters, and I'm using the Y and Z coordinate as well. So this is a power law, 1/7 power law for the inlet velocity. And here you see you also have some help here if you want to use some constants, some variables. So there's a lot of help to sort of improve that. I'm going to click OK. I'm going to go to the inlet big here. And instead of 1 here, then I'm going to go to an expression here. And I could simply just click 1 meters per second here and simply just write my expression if I wanted to do that. So right now it accepts this, and this would be 3 meters per second. But what I can also do is I can just write this vterp, and that way it refers to this named expression that I generated here. So let's go OK, and let's go to the solution and calculate a couple of iterations. Let's just take 15. Oh, before that, let's plot some vectors just to show you on the inlet, just to show you how it looks. So here we have the velocity profile. I'll quickly do a snagget of this. So we have that for later. And then we're going to calculate a couple of iterations with this expression. This would have been a lot faster if I'd activated some parallelization, but we'll live with this. There we go. Okay, so now we'll look at the vectors again. So here you see that you have a lower velocity, near the wall than we had before, and a higher velocity in the middle, or not a higher velocity in the middle, because then I would have to change the expression a little. But you see that you now have a velocity profile instead, just by implementing the expression that I did. So yeah, so now that's actually what I wanted to show. That sort of concludes the demonstration, and I'll be going into some questions now. So let's see what we have, if there is any. I think so far I've had one question, which is it necessary to go through all steps if your geometry is ready for CFD? You don't need to extract fill your volume. No, if you always need to do the surface. If you use the Fluent meshing, then you always need to do surface mesh and then volume extraction and volume meshing. But if you have a watertight geometry just like the one that I had, then those tasks would be very quick. But it also eases up the task when you want to sort of change your mesh or refine your mesh in certain regions. Then it's much quicker to do a surface mesh than to do a full volume mesh. So that way it's sort of mixed up for that task. But if you have if you've done this workflow, then you can then you don't need to do the tasks again. Then you could sort of automate that process. Yeah. Okay. So I don't see any more questions. Yes, there's another question here. Can the VOF-to-DPM model go both ways, from discrete particles to VOF depending on the volume fraction? For the first release, it couldn't, but I'm quite sure with the new release that's coming that you're able to do that as well. Yes, and also to use wall films, for example, if you want to do that. But for the release we have now, I don't think so. But yeah. So that's a part that's been discussed as well. And the next question, can you combine this VOF-to-DPM with reactions? I don't see why not. I think this is a bit specific, and I haven't used that model a lot myself. So what we can do about that is that we can email and I can send you some more information on the model, sort of the also guides. There's some best practices on that specific models that I can provide you. Yeah, and anybody that's interested in that can simply just send me an email. Yeah, if you don't have my email, then let's see here. I'm not sure if it's showing you on the webinar, but then I can simply give it to you here. Oh, there we go. Team.hübschwein@EDRMedeso. All right. But I guess that's it. Thanks a lot for joining, and remember to tune in for the 2 other webinars this week. We have one about electronics, and we have one about the structural parts of ANSYS. So yeah, everybody have a nice day. Thank you.